Okay, so we are looking at section 2.4 on complex numbers. The learning objectives are to use the imaginary number I to write complex numbers, perform operations with complex numbers, and find complex solutions of quadratic equations. But we're going to start with a brief history lesson of numbers. All right, the first numbers that were really used by people were whole. Well, I'll say counting numbers, right? Whole numbers kind of include zero. Zero came later. But when people wanted a way to describe how 4 people could split up 31 bushels of wheat, they would need what kind of numbers?
Fractional counting.
Fractions, rational numbers. All right, so rational numbers came about. When people wanted to express nothing, they had to invent what?
Zero.
Zero. That was not an easy concept for people. That came later. When people wanted to attach a number to a problem like I have 2 sheep, but you owe me 13 sheep, they needed to come up with what kind of numbers? Negatives. Yes, this is a true history lesson. When people wanted to have an answer to a problem like this, they had to come up with what kind of number?
Trigonometric.
There you go. Starts radical. I.
Imaginary.
Irrational. Irrational. Thank you, Joe. No, because the solution for this would end up being a radical, right? So they had to invent irrational numbers. So that brings us to, well, my point, which is anytime a new problem came up that people wanted to solve with math, they would have to expand their knowledge of numbers or invent numbers to help them answer questions. So when people wanted to solve a problem like this, they had to come up with a new set of numbers. And they actually came up with a set of numbers that were so controversial at the time because people thought they're not the numbers that we're used to. These are like imaginary numbers. And unfortunately, that name stuck. But there's nothing pretend about these numbers. They are used in real life, okay? And you're actually going to write me a little paper about how they are used in real life. All right, so let's solve this one right here. If we were going to solve this equation, x squared plus 1 equals 0, we would subtract 1 from both sides. We get x squared equals negative 1. And then we're going to take the square root of both sides, plus or minus. And we're going to get x equaling plus or minus the square root of negative 1. Now, you've always been told you can't have a negative number under a square root radical. But you can if you don't mind stepping outside of the real number system. All right? So what we have here is we're going to call this the number I. I is the imaginary unit. All right? So x equals square root of negative 1, where negative 1 is equal to I, and it's called the imaginary unit. If we square I, we end up getting negative 1. So I squared is equal to negative 1. All right? So the set of complex numbers is the set of all numbers that has a real number added to a multiple of the imaginary unit.
So when you say that I is equal to square root of negative 1, does that mean that plus or minus is that square root of negative 1?
No, I is just defined as the square root of negative 1. And if we throw a negative in front of the square root of negative 1, that would actually be opposite of I.
Oh, yeah.
All right? Okay, so let's take a look at some examples. If you remember back in August, probably day 1, I made a Venn diagram with you about the real numbers. You could look back at your notes from day 1, and you probably would see a Venn diagram. Well, I want to expand on this Venn diagram by looking at a Venn diagram of complex numbers. All right, all the numbers you've ever worked with in your whole life have all been on this side of the complex number Venn diagram. Every number you've worked with have been real numbers. All right, and back in August, we probably had a little subsection under the reals for the rational numbers. And we had a subsection under that for the integers. and we probably had a subsection of that for natural numbers or whole numbers and so on. So my point is, just to remind you how Venn diagrams work, if I want to put the number 2/5 in my Venn diagram, it's not an integer, but it is a rational number, and of course it's real, but if it's rational and real, it's going to go right there. Everybody remember how Venn diagrams work? And if I have a number like -7, well, that is an integer, and it's rational, and it's real, so it's right there, right? And if I have a number like pi, that is irrational, it's not rational, it's got to be out here. So now we're adding to this, we're adding numbers like 3 plus 5i, or -7 minus 2i, or 4 plus 0i, or 0 minus 6i. All right? 3 plus 5i is an imaginary number. It's still a let me make sure we're all understanding this. Every single number I put on here is a complex number. Pi is complex. 2/5 is complex. -7 is complex. But really, we didn't think about the fact that -7 is really -7 plus 0i. 2/5 is really 2/5 plus 0i. It's got a real part, but the imaginary part is just 0. It's just knocked out. All right? So if I want to plug or put -7 minus 2i in my Venn diagram, that would go over here, for example. But 4 plus 0i, where's that going to go?
What?
Yeah, it's going to go on the real side. That's actually going to go in here with the integers. Shrink you take that down. Because it's really just equal to 4.
Because it's 0 times I.
It's 4 plus 0. So really this -7, I could really write that as -7 plus 0i. You with me?
Yeah.
And, right, and that would go up here too. Everybody with me?
Yes, indeed.
Dan?
So, okay, this is going to be really bad, but is 2/3 rational or irrational?
2/3 is rational because it can be written as a ratio of integers. So 2/3 is a rational number. Okay? And
I'm probably jumping ahead a little bit, but if we had 2i, would that be the same as 2 times the square root of -1?
yes. Yes. Okay, so where to put this one? We already talked about that. That's going up here in integers, right? Where to put this one? Well, this one doesn't have a real part, but it does have an imaginary part, so we would call that a pure imaginary number. So 0 minus 6i is really just -6i, and so that would go in the separate little subcategory of imaginary numbers. But remember, these are all what kind of numbers? Complex numbers. All right, that leads us to simplifying complex numbers. So we want to simplify the square root of -16. We're going to split this up into square root of -1 times square root of +16. Square root of -1 is what? I. That's our imaginary unit. And square root of 16 is 4. So let's just write our answer as 4i. We're going to put the number in front of the I.
So that's the answer?
That's our answer. That's simplified. All right, what about square root of -75? Can you take a moment to simplify that, please? Nick? Go ahead.
Alright, so you're gonna multiply the square root of -1, and then square root of 75. And then so square root of -1 equals the imaginary unit I
Okay.
times 25.
Square root of 25?
Yeah, square root of 25 times 3.
Square root of 3?
Yeah,
So we get I times
5
times.
square root of 3.
All right, and so we're going to write that as, let's leave the things that are in front of the radical together, but let's put the 5 first. So we got 5i times square root of 3. Are we okay with this? All right, let's talk about whether when two complex numbers are equal to each other, that just means that the real parts are equal and the imaginary parts are equal. So if a plus bi is equal to c plus di, then the a has to equal to c and the b has to equal to d. So if I give you a problem like 7 plus 8yi is equal to -6 4x plus 12i. Can you solve for x and solve for y? Can you find x and y?
No, can't.
We're going to set the real part. Since I got one complex number equal to another, I know that the real part here has to equal the real part here. Notice the real parts are the parts without the I, right? So if 7 has to equal negative 6x, then x must equal what? 7 over negative. So x has to equal 7 over negative 6, negative 7, 6. And what's the y going to equal?
3/2.
The 8y is the part that's being multiplied by the I. So this is my imaginary part, has to equal the 12i. So that means 8y must equal 12. So divide by 8, and I get y equaling 12 over 8, which is 3 over 2. So I get 3/2 as my y, negative 7 as my x. Are we okay with this? All right. And that brings up operations with complex numbers. We are going to learn to add, subtract, multiply, and divide complex numbers. If we're adding, all we do is we add the real parts together, and we add the imaginary parts together. So can you give that a try for us, Noah?
3
3.
plus 4i.
3 plus 4i. Do people agree with that? Okay. And if we're subtracting, then again, you're just going to combine the real parts and combine the imaginary parts. But I strongly suggest that you change this minus to a plus, but then change these signs here, so you're really adding the opposite. All right, can you now add those two new complex numbers together? Arya?
7 minus 8i.
Do people agree with that?
Yes.
Is this okay? All right, so that's an example of adding and an example of subtracting. Let's try multiplying. If we're going to multiply, this is really like a pure imaginary number times, just a general complex number. We can distribute. Can you talk me through that, please, Christian?
Would it be 20i
20i
minus 8i squared?
minus 8i squared. We talked about I squared. What's I squared equal to?
-1.
Negative 1. So whenever you see I squared, you're going to replace it with a negative 1. So I'm going to have 20i minus 8 times negative 1. Is that plus 8?
It is.
And we're going to actually write it as 8 plus 20i, because we pretty much always want to write our complex numbers in this form. A plus bi, real part plus imaginary part. So here's our final answer for this one. Let's do another multiplying. Eddie?
So would you just consider like I just like x as just a variable?
You often treat it like it's a variable because you can combine what's 2i plus 3i, it's 5i, and so on. It's not a variable, right? It actually stands for imaginary unit, square root of negative 1, yes. But in operations like this, you can treat it as if it was a variable. Okay, we're now multiplying two complex numbers together that are both in the a plus bi form. Can you help me out with this, Gabe?
I suppose.
Thank you.
We could just do FOIL, right?
Please do.
So that would be 15, and then it would be 12i on the outside, and on the inside it would be negative 5i, and then on the last it would be negative 4i squared.
All right, and can you clean that up for us, Nick?
All right, you can combine it like terms.
Okay?
So you're gonna have, just to rewrite it, the whole thing, 15 plus 7i minus 4i squared.
Minus 4i squared.
Oh, that's a negative 1, so
Okay.
that's plus 4.
So really a plus 4. Are we okay with this?
Yeah.
And so our final answer in a plus bi form, Vincent?
7i plus 19.
Let's put the real part first, though.
Oh, 19.
19 plus 7i, are we okay with this? All right, let's take a look at this one. Would you do 2 plus 4i times 2 minus 4i? Everybody work on that, please. Give you 30 seconds to multiply that out. Are you noticing anything interesting about this one? Dan Bosworth,
You're gonna get a whole number as your final answer.
what, no imaginary part?
No.
What happened to the imaginary part?
They cancel out, they subtract off.
Subtract it off. All right, so if we try FOIL on this, we get 4 minus 8i plus 8i minus 16i. The imaginary part subtracted off, oops,
That's
screw up.
squared, that's
I
squared.
squared, so this is equal to -1, so I get 4 plus 16, are we getting 20 as our answer? Okay, so what I want you to notice is that the product of two complex numbers can sometimes be a what? Real number. Can sometimes be a real number. And what's the special case? What's going to allow them to be, the product to be a real number is if you're actually multiplying complex conjugates like you just did. Complex conjugates would be a plus bi and a minus bi, where the real parts stay the same, but the imaginary parts are opposite of each other. Yeah.
Would that not be like our difference of two perfect squares? Because I like noticed that right away, and so like I just went to that. I didn't even like FOIL.
Sure. So, yes, so difference of two perfect squares, you could think of it that way. 2 times 2 is 2 squared minus what? A 4i squared, right? Because this is kind of like a plus b times a minus b.
Yeah.
Yeah, and that is going to get you right to this answer. That's true. But if we're talking about multiplying two complex numbers that are conjugates of each other, we're guaranteed to get a real number, is our answer. Eddie, are we okay with this?
Yes.
Focus.
Excited.
All right. So we talked about complex conjugates. All right, let's skip on to this. To divide two complex numbers, now we're talking about dividing. All right. To divide two complex numbers, and you want to write the answer in standard a plus bi form, you're going to need to multiply the numerator and the denominator by the complex conjugate of the denominator. So what is the complex conjugate of our denominator here? Trent. So complex conjugates are going to be a plus bi and a minus bi.
Okay, so it's -6 plus 3i.
Well, that's what we have.
Yeah.
-6 plus 3i. So what's the complex conjugate of -6 plus 3i? You keep the real part the same. You make the imaginary part opposite.
3i.
Say that again.
6 minus 3i.
Then you switch both. We don't want to switch both. You got to keep the real part the same and make the
Okay, so
imaginary part.
-6 minus.
-6 minus 3i. So what we're going to do is we're going to multiply this fraction by -6 minus 3i over -6 minus 3i. -6 minus 3i is the complex conjugate of the denominator. And what we just saw is if you multiply two complex conjugates together, you end up getting what type of number?
Oh, real.
Real number. And that's what we need if we're trying to rewrite this in standard a plus bi form. So in this case, would you please take a moment to multiply your numerators together using FOIL, multiply your denominators together using FOIL or the a plus b times a minus b technique for difference of two perfect squares, and see what you get for your answer.
Is there like any way to do these on a calculator?
Oh, yes.
What size of line?
There is, and we'll talk about that, yes. But I do want you to be able to do it by hand as well. Dana?
Should we simplify the I squared and the numerator and denominator before we do anything else?
You will certainly need to, anytime you see I squared, you're going to rewrite it as -1.
Gotcha.
All right, talk me through your numerator here, Carter.
Numerator I had 5 times -6 is -3.
-30.
Then you get negative 15i,
Negative 15i
12i,
plus 12i
and then plus 6i squared.
plus 6i squared. And talk to me about the denominator, Hannah G.
You get 36 minus 18i plus 18i minus 9i squared.
Minus 9i squared. Do people agree with this?
Yeah.
All right, can you clean up this fraction for us, Kathleen?
So for the top, it would be negative 30, and then minus 3i, and then I squared is negative 1, so we minus 6.
This part is negative 1, so that's, what did you say, minus 6?
Yeah.
Okay, so that looks like we really have, what, negative 36 minus 3i? Does that look okay? And can you clean up the denominator for us, Max? Well, what have you been doing all class?
Listening.
You guys hear applause. Time out.
Okay, we are back.
Shout out
At
to
this
Danny
point,
Software.
we're cleaning up this denominator.
Love you, Zach.
Max, you got something for us? Can you combine any like terms here?
36 minus 9i squared.
All right, because these are gone, so we got 36 minus 9i squared, but I squared is equal to what?
Negative 1.
Negative 1, so we end up getting what in our denominator?
36 plus 9.
36 plus 9, which is
46.
45. So let's write our final answer as negative 36 minus 45 minus 3 over 45i, because we want to write it a plus bi form. So our a is this, which we can reduce to what? Is that negative 4/5? Yes, 9 goes into both of those? Does that look right? And then the 3 over 45 can reduce to 1/15i. So my a is negative 4/5, and my b is negative 1/15. Here's my answer. Does this look okay? Charles. Okay, so at this point, I'm skipping that. I want you to practice what you're going to need on the quiz in about 10 minutes by solving this using quadratic formula. Go.
Am I just gonna stay right here?
X equals negative b plus, oh, am I recording? Let me pause. No, I'm just going to say x equals negative b plus or minus the square root of b squared minus 4ac
All over 2a.
Okay, go ahead and do that, please.
Wait, are we allowed? Yeah, let's go. Any specific way you want to solve them on the quiz? Like, do we use quadratic formula if for like all of them if we want to?
No, because sometimes they'll say solve by factoring, or maybe they'll say complete the square, put it into, standard form and so on. Is that phone?
Shout out to Lex. Hope you're having fun in school.
She's not recording
Why?
anymore. She's totally recording. But cut all this out. Am I going
Okay, let's see how you did on this.
Wait, I got a negative.
We are doing negative b plus or minus square root b squared minus 4ac all over 2a. So you should have written negative 14 plus or minus square root of 14 squared minus 4 times 8 times 9
Breaking news.
over 16.
Doesn't work.
So
No, we just learned how to do it.
Non-real. Oh, why you gotta do that to me?
That is so much fun.
So the reason why Dan got non-real calculation is because this number that's underneath the radical is negative. Agreed?
Yeah.
So what does that number turn out to be?
Negative 92.
Thank you. So I get negative 14 plus or minus square root of negative 92 all over 16, which I'm going to split up so I have two separate fractions like this. Are we okay with this? I know that negative 14 over 16 can be reduced to, is that negative 7/8?
Yep.
And then can we simplify square root of negative 92 like we did in, whoopsie,
Oh.
no, I don't even know where it was.
Yeah, 92.
Was it
first
here?
page.
No. Was it here? Yes, like this, right? So how are we gonna simplify?
I got it.
No.
What do you got?
Alright, you can do, so you can have, square root of negative 1 times square root of 92
Uh-huh.
over 16.
And any perfect squares going in 92?
4 and 23 can.
4 times 23, so I'm gonna write this as square root of 4 times square root of 23. Square root of 4 is
2.
2, so I got 2 times square root of 23, but don't forget I also have,
Your square root
which
is
is
I.
I. So it looks to me like I would write my answer as negative 7/8 plus or minus 2I rad 23 over 16. Does that look okay?
Yeah.
And then I can reduce this 2 here with this 16, and I think I like my final answer as negative 7/8 plus or minus square root of 23 over 8I. Something like that, Dan?
Sad story, you forgot to use an recording.
I don't think he did.
She never
I don't
stopped.
think
She did stop, but she stopped.
She's still going.
We're still going.
Oh my
Yeah,
God,
Bob,
what?
everyone.
Hi, Bob. Hey, what's up, baby?
Hey, Zach.
We have a question back.
Hi, thank you.
Can we go back one?
Scroll down a little bit.
Scroll down.
Hi, Dad. Hi, Dad.
Okay.
Hi, Cam. I say calculus, though.
All right.
How did you get to I?
Because the square root of negative 1 times the square root of 92 was I times square root of 4 times square root of 23. Square root of 4 is 2. Square root of 23, we can't do anything with it. All right, questions on this? Okay, last thing, I want to get back to this one. For here, it says, can you find a pattern? Focus, please. If you have I to the first, we know that that's just equal to I. I squared is equal to negative 1. I to the third is really I squared times I. So wouldn't that be just negative 1 times I?
Negative I.
So opposite of I, sure. And how about I to the fourth? Well, that's I squared times I squared, so that's going to be what? Yeah, negative 1 times negative 1, which is a positive 1. How about I to the fifth? Well, that could be I to the fourth times I to the first, but I to the fourth is 1, so I get 1 times I is I,
It's gonna repeat.
and it's starting to repeat. So every 4 in our pattern, it's going to repeat.
No.
It's going to repeat. So the pattern goes like this: I, negative 1, negative I, 1. I, negative 1, negative I, 1. I, negative 1, negative I, 1 for I to the...
Let's make a rap.
Yeah.
Okay, so if I ask you, last question, then we're taking this quiz. So if I ask you to find I to the 33rd, I don't want you to make the list all the way down to 33. I want you to be systematic about it and say, well, I know that it's every multiple of 4 as a power, it's equal to what? 1. So what's the closest multiple of 4 to 33?
32.
All right, so I could write this as I to the 32 times I to the first, and I to the 32 is what?
No, I want
1, because it's a multiple of 4, so I get 1 times I is I. Are we okay with this? All right, so I'm going to stop there. I need you to, thanks for watching.
Bye, Kevin.